Welcome to the Cosmic Pie Podcast, Season 4, Episode 21. And I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
Robert.
Yes.
First time since vacation. How you feeling, buddy?
I'm feeling pretty good. It's a little weird being back in this chair, but I think we'll get through it. Hopefully there'll be a few people tune in and watch the video too.
And just to warn people, we do have new equipment.
Yep.
So there may be some hiccups on the way, but we'll see. The other thing to warn you about is you might hear some backup noises.
Yeah.
Right this time of the year, the construction of our new STEM building, science, technology, engineering, math, is happening in full force just across the street from us.
Yep. It's construction season.
It's construction season, but we're getting something more than normal, right? We're getting a brand new multi-million-dollar complex being built here on campus. And hopefully it's going to be the most beautiful building on campus for many years to come. Yes, Robert.
Yes, it will.
And it's also another reason to come visit us here at the University of North Dakota here in Grand Forks.
It'll definitely be the most advanced and modern building on campus for, at least a few years.
And I can't wait till it's done, too. It's going to be nice to go through to see all the new, teaching areas, research areas, all that kind of stuff. It should be beautiful. You know what make it even like the best, like the cherry on the top sort of thing?
Are you referring to the on the top part?
Yeah.
Yeah, it would be nice if there was a telescope up there.
It would be. And it could be on campus, very easy access for students, especially to teach them, astronomy-related labs and these kind of things, do observations of the night sky. But it is what it is. We do the best we can. And if anyone of you out there, have a lot of money and you like to... Well, first of all, we should do the disclaimer, Robert.
We should do the disclaimer, especially now.
Go ahead, Robert, old buddy.
All right. Oh, you're going to put me on the spot again. The opinions and everything that are expressed in this show are those of myself and Wayne, and not to reflect the opinions of the University of North Dakota, the College of Arts and Science. It's just us, folks. We're here. Yeah.
And we're not begging for money. It's just if you have some.
Yeah.
It'd be nice. But that's the one thing that, as a public university, we rely, of course, on taxpayer money.
Right.
And so that's extremely important. But we also rely on people and their generosity. And we really appreciate all of the donations that have been made over time, including donations in our own department.
Right.
We benefit a lot from people who have done that. And so if you're out there, if you're thinking about it, maybe you're doing up your will and you had a really good time, or let's say you developed a career that had a major impact by going to the University of North Dakota. That's kind of some of the things you might want to think about,
And I will throw this out there. Having been part of, let's see, what is it now? 1, 2, 3, 4, 5 different universities, 6. Physics departments really are not, unless you are at a MIT or Case Western or somewhere, they're generally not that well funded. Most people look at physics and go, "Oh yeah, that's hard," and that's about all they know about it. So, yeah.
Yeah, we do the best we can, obviously. But for those who are interested in in science in general and the different fields, we do rely on donations. It would help a lot. I'm not begging for money. I'm just saying you can do what you do with your money, but please keep us in mind. Keep us in consideration, obviously.
That's why I made my comment as in general, because check with the physics department at your local university. I'm sure they would appreciate any help that they can get as well.
And the other thing, I'm going to make a promise here today, and you can, we have this recorded, so you can play it back to me. If I was to win, if I was so lucky to win the Powerball, which is well in excess of $300 million right now, I will donate to New. In fact, I will not donate. I will ensure that a nice size 1-meter telescope observatory gets constructed and put on the top of the new STEM building. I'll pay for the whole thing.
Yeah.
What do you think of that?
I'm right there with you. There are definitely some plans that involve scholarship funds and equipment donations to several of the universities I've been associated with.
Exactly.
Simply because it's the right thing to do.
Yeah.
You know.
Now, we do have a live chat feature, so if you have any comments or questions, if you like to disagree or agree with Robert and I or whatever it is, please feel free to use that. And also, don't forget, we do upload our podcast the next day on Spotify. So if you'd rather listen to that, or better yet, listen to us live now or listen to us on YouTube, and then go listen to us on Spotify and see if we say the same things.
And now I'm sitting here thinking of the Saturn eyes. Listen to us live now or listen to us live later.
Exactly. Okay,
sorry.
so our first slide of the day, our first news item.
Yeah.
And remember, this is the fastest hour in podcasts, right? When we talk
Right.
about this stuff, it goes extremely fast. But today, we're going to bring back your favorite, Robert. We're going to bring back, you know what it's coming, 3I Atlas.
So what's going on with it now?
Okay, just in case you haven't heard, 3I Atlas was this comet that was discovered essentially about a year ago.
Mm-hmm.
It was reported on July the 1st of 2025. And what struck everybody's sort of attention in some sense is the fact that preliminary orbit calculations showed that it was on a unbounded orbit around the sun, a so-called hyperbolic orbit. That is, it came from outside the solar system, would make its closest approach to the sun. And that closest approach, by the way, was like the average distance of Mars to the sun, so it really wasn't that close. And then it's heading back out of the solar system, never to return. So this was sort of the third of these type of objects that we discovered in relatively recent times. And so the object, all observations showed, was a comet. So it's been labeled as a comet, an interstellar comet in that sense. And there was some talk out there, what we call in the old days scuttlebutt, that this object may not be a comet, that it may be a UFO, actually an alien spacecraft disguised as a comet.
Right.
And it was kind of probing, our solar system and other solar systems as well. And there were some out there that were kind of pushing that idea for various reasons. And you can make up your mind or contemplate what those various reasons were. And so, to be fair, that extra attention definitely got the attention of astronomers around the world. So anybody who had access to equipment that could provide additional information of the true nature of the object itself definitely seemed to do just that. And there have been a large number of professionally published papers that have come out in the last several months, including the one that I'm showing here that's due to be released. Well, it's released now, but they put the date on it as July 2026. And the paper describes observations that was made by the Allen Telescope Array, which is an array of several radio dishes in northern part of California. And those dishes are part of the SETI program. That's the Search for Extraterrestrial Intelligence. And the idea there is they would sit back and sort of monitor the comet, i.e. comet, right? Whatever it happens to be. And if for some reason it was an alien spacecraft, that potentially there would be some type of, electromagnetic signal that would be given off by the spacecraft, and that we would be able to detect it at radio frequencies. And so they stared or made observations of the comet for about 7.25 hours, which is quite interesting. And you wonder, because of that, did it detect anything? Was there no detection, or was there some type of radio detection that's due to the inherent nature of the object itself? That is that, in general, comets will release some type of electromagnetic radiation at radio frequencies. And the next slide kind of illustrates what they actually observed. And what they observe is the fact that there are actually well over 73 million detections or signals coming from the direction of this comet itself. So it's essentially 74 million. So it's not like they detected nothing. They detected a lot of stuff.
Yeah, but what are these detections?
That's the main thing. So the slide here shows you the detections. And because things are in motion, the comet is in it's moving through the solar system, of course. The Earth is rotating, the Earth's also going around the sun. So there's all these motions involved. And in standard physics, we know that if something, let's say, is producing waves, that the actual observed wavelength will depend on the relative motion of the observer and the object or the source of the waves, the so-called Doppler effect. And so because of that, you would expect that things would move around, and radio astronomers call that the drift rate. And in this case, it is the change in the frequency with respect to time due to the relative motion of the Earth, or the telescope in this case, which is on the Earth, and in this case, the target being the comet. And you can see those type of signals in this diagram. The change in the wavelength could be both an increasing wavelength or a decreasing wavelength, depending on that relative motion. And that's what you're seeing sort of in the horizontal scale here, the axis, both negative and positive values. Now, the one thing to notice in this slide is you get the peak, that is the highest point, if you like, is essentially at the 0 marker. And the reason for that is because, and you can read the caption there that kind of explains that, is because most of the incoming signal is in the same reference frame as the telescope. That is, it's on the Earth. So that's definitely due to non-cometary emission. That is due to sources on the Earth itself.
It's
now,
noise.
Yeah, so there's lots of contamination. These radio telescopes have side lobes, as we call it, so that you can still detect something even though you're not pointed directly at your target. You can get signals coming in essentially from the side, if you think of a standard sort of parabolic dish, and those are the side lobes. But if you're staring at some object in the sky, let's say, and you're getting a signal coming in from the side, chances are that's not from your target. I can think of an extreme situation where you get reflection of the radio waves and they might come in through the side lobes, but in general, it's earthbound sort of contamination that you're going to pick up. The other thing you worry about, Robert, is when you look up at the sky at night, and especially just after it gets dark, what can you see?
Satellites.
Satellites. So,
Lord at the satellites. Oh my goodness!
Compared to what it was like
wow.
just 2 decades ago,
you don't even got to go back 2 decades. It was a rare sight when I was at West Georgia. So 2007 to I think 2011, it was a fairly uncommon sight to see a satellite. Now you'll see dozens. It's ridiculous.
And of course, companies like SpaceX with their Starlink system and other companies that are launching satellites, trying to get into that market of the internet access, and you have them in low Earth orbit because of the latency of the signal. You want to bounce signals up to the satellite and back down to Earth as fast as possible type of thing. So you shorten up the distance because you're always limited, of course, by the speed of light.
Yeah.
That means you're getting a lot of stuff that's moving across the sky at any given moment. And I'll put this out as an exercise or something fun to do, is go out any evening that's clear, look up in the sky, and see if you can see any of these satellites. And if you look carefully, they're all over the place.
Yeah. If it's moving relatively quickly, and if you ever spot one, you'll see what I'm talking about. It's moving at about the speed that a jet does across your field of view.
Yes. And
except it won't be blinking.
That's it. That's it, right? And then, of course, most of the time when you're looking at an airplane, you actually hear the sound from it anyways.
Right.
And these, of course, would not make any sound at all. And the other thing you'll notice if you look carefully, and it's not your eyeballs that's playing tricks on you, it's actually real. You would think that when a satellite is crossing your sky locally, that you'd see this nice curved path like across the sky. And that's not actually what you get if you look very carefully. What you'll notice is that the satellite seems to jump, like make these small little minute jumps from one side to the other. And that's just due to the refraction of the light as it's passing through the Earth's atmosphere, what ultimately is responsible for the twinkling of the stars. So you can actually see that. And you don't see that with airplanes because airplanes are not above all of that atmosphere like the satellite is.
The other thing that will distinguish a satellite is over a relatively short period of time, most of them dim. Noticeably get dimmer and dimmer and dimmer until you can't see it anymore.
Yeah, so that's a good point, Robert. Some people say, how can I see a satellite? Does it have lights on it? No. What's happening is that they're up high enough that they actually would see the sun if you were on board that satellite. And then the sunlight reflects off the surface of those satellites, and some of that light would be reflected down towards the Earth. So if you're in the right location on Earth and the satellite's in the right spot where it can reflect that sunlight, that's what you're seeing, reflected sunlight.
Yeah.
And
but it moves into the shadow of the Earth.
yes, that's right. And so what happens is eventually it will just like disappear and you can't see it anymore. And that's because it's not reflecting sunlight back to your location. And you can see that easily. You go on the web, there's different places to go to, like where is the International Space Station? Because that's a fairly bright target because, number one, it's large, it has highly reflecting solar panels on board, and it's also in low Earth orbit.
Yeah, it's only 400 kilometers up.
Yeah, so that's a really bright sort of object to see. And there are places where you could say, given your location, where you're located, at what times can I see the International Space Station? And you'll get usually times and dates to be able to look it up. And it's worthwhile doing. It's actually cool to see it. Mm-hmm. So anyways, what do you do with all these signals? Well, you have to have some kind of software that kind of parses through those signals to extract the bogus signal, that is the non-cometary signals. And in fact, the next slide kind of illustrates the game here. Well, we have plotted as the number of signals, and notice that the vertical scale is a logarithmic scale, not a linear scale. And on the horizontal axis, we have the signal-to-noise ratio. And what you see there when you're on the far left, that's for very faint signals, that you can tell that the vast majority of the detections are of the low signal-to-noise ratio type of detections. Once again, implying that a lot of this is probably extraneous sort of reflections off the surface of the Earth into the side lobes of the telescopes.
Could be charged, the solar wind interacting with the magnetic field.
All
sorts of things.
Yeah, and the detections of some of the satellites are there, but they're not a large number of them, right?
Right.
And they're usually going to be a high signal-to-noise ratio. They're going to be noisy in general, not always the case. So a lot of these detections then are of these very low signal-to-noise ratio type of sources. And the conclusion is that nothing of extraterrestrial in nature was detected coming from Comet 3I Atlas.
Yeah.
That's the conclusion. Of course, you can only say down to a certain, flux level, as we would say in radio astronomy, a certain brightness level at radio wavelengths. So there could be something, it was just too faint to be picked up by the instrument that we used.
Yeah, but if it's that faint, it's probably not detectable at any distance from us. It's going to be part of the background of the galaxy and things like that.
Yeah, and you can always make the argument that if you are a smart, highly advanced society of life forms, would you be broadcasting if you're near in a solar system where you probably know there's life on the third planet from the sun?
Right.
Would you rather keep yourself hidden in that sense and just go along with the notion that, anyone there was going to think that we're just a comet if we don't broadcast?
Right.
So maybe you could always argue that. But every observation that we've made is all consistent that this object is just a comet.
Yeah.
But it's fun to speculate.
Interstellar comet? Yes. But it's still a comet.
Yeah, and it's fun to speculate. If we were to send probes to other solar systems and we had maybe an inclination that there were life forms, maybe we picked up some of their broadcasts or something like that, would we try to go through and do a sort of, a search mission to see what was there, reconnaissance mission, but try to do it incognito, right? So nobody knows we're there type of thing.
Yeah.
And probably the answer would be yes, right? Until we know what we're dealing with before we kind of say, hey, would you like to shake my hand type of scenario. Right?
But what I'd like to point out is a lot of people are crying, why isn't this even being investigated? This paper and this study show it is. It has been. And nothing's being found to indicate that it's an alien artifact. So,
Exactly. And we'll see what happens. But of course, now that the Vera Rubin telescope is sort of almost at the point where it's running, like optimal peak efficiency, they're still going through some engineering stages of it and tweaking things. we're going to get a lot of these things discovered.
Oh,
That's
yeah.
going to happen. So there's going to be a whole cottage industry out there that's going to form just trying to, do the follow-up study of these type of objects.
It's like exoplanets. We found one, then we found another, then we found 5, then, and so now we're up to what?
It's like 6,000 or so in that order.
It's more than that by now.
Yeah, but it's in that ballpark, right?
Yeah, it's right around 10,000. I'm pretty
and you need
confident
to
saying
and
that.
you need to follow all these things up in detail. That's what takes the longest time, of course, right?
You need at least 2 detections, or it's not considered an exo. So
Yeah.
But to me, the point is that once we started looking and had the equipment to look and knew where and how to look, we found them everywhere. So these interstellar objects, the same thing's going to happen. We now know how to look, we know where to look, and we have sensitive enough instruments to pick them up. We're going to start seeing them.
And it's kind of the rule of thumb that's happening, for many decades now in astronomy, essentially since the space age, and one could argue since the time of Galileo in the 1600s, is anytime we have a new instrument or instrumentation, we discover new things.
Right.
And one of the things that was discovered back in the 60s, and this was done initially by the military, was the so-called gamma ray bursts.
Oh, yeah.
So what happened was both the Soviet Union at the time and the United States put together satellites in Earth orbit that would look down on each other's country. And one of the signatures you're looking for, if you have these sort of nuclear test ban treaties where people are not supposed to be lighting off nuclear weapons, is you get this sudden burst of gamma rays that are emitted in the explosion. And these can be detected by satellites. And the story goes that when these military satellites were first put up, these gamma ray satellites, they started to detect these bursts of gamma rays. And of course, if you think about you can imagine scientists saying, oh my God, the other country's violating this treaty. And what it turned out, though, is because of directional information, that is, you build a detector that can actually tell you in which direction the gamma rays came from. They didn't come from Earth. They came from behind the spacecraft out in the deep space.
Right.
And so eventually this information was passed on to the scientists, people at NASA and so on, and they put together spacecraft. Then above the Earth's atmosphere, we get a nice, a view of these gamma rays that are going to be coming from space. And they discovered that there were these flashes, if you like, of gamma rays that only lasted sometimes, a fraction of a second to several seconds to even extreme examples of minutes, coming from seemingly random locations on the sky. And the biggest mystery was, are these things within our own galaxy somehow producing these gamma rays, a very high energy burst of photons? Or are they really, truly extragalactic, like they were coming from outside of our galaxy, maybe from other galaxies? And one way to figure that out is to actually just plot their location. So if you observe long enough and gather enough data and you plot where they were located, they were coming from all different parts of the sky, which leads support that they were coming from other galaxies.
Right. Because you got to remember, our galaxy is a flattened disk. So if they were coming from within the galaxy, you would expect them to be clustered in that disk.
Yeah, you'd be able to see them along where the Milky Way is if you're at a dark location looking up at the sky on a clear night. But that's not what happened. So we knew they weren't just coming from the Milky Way. They were coming all over the place. And so we label these as cosmological sources. And of course, we got smart and put up better telescopes that had the ability to observe not in just gamma ray wavelengths, but also in optical wavelengths and even X-rays. And when these bursts go off, as we called them, we had other ways of observing those locations on the sky, and some of them were tied into other galaxies. We could actually observe in optical the galaxy itself. In fact, a lot of these objects that were closer were tied in to supernovae events.
Right.
So today, the general understanding is a lot of these gamma ray bursts then are associated with these really high magnetic field, these magnetars as we call them, that are these massive stars that core collapse. And in that core collapse, they actually can beam radiation out, just like in the form of jets, collimated jets. You have to have a very, very, very strong magnetic field for this to occur. And then along with that mechanism that creates then this burst of EM along these jets, not only do you produce optical light, but also other frequencies, including at the gamma ray wavelengths.
Now, I'd like to point out, gamma ray telescope is kind of a misnomer in my opinion, because you can't focus really gamma rays. So basically what you're doing is putting a big block of lead in the space with a detector in the middle and observing the cascade of particles that explode when the gamma ray strikes an atom.
Yeah, and that's, I mean, not to get into technical details, but that's how we can tell which direction they come from. You have essentially, if you want to think of it, tripwires.
Right.
And these wires get triggered, in different parts of the detector. And if you see it, the wire that was triggered in one side of the detector, then a bit further in, and then further in still, and so on, then you get an idea what direction then that gamma ray was coming in at. And it's usually like germanium crystals, where the gamma ray photon gets embedded inside of the crystal before it eventually interacts with the atomic structure of the crystal itself, and that energy dissipates within the material.
It's fun stuff. It's one of those things you really, if you're interested in this sort of thing, this is some of the fun stuff that you can get into and learn. So
now, the reason why we went into this discussion about gamma ray bursters is because a very nice telescope that was put up several years ago by NASA, initially known as the SWIFT Observatory, its purpose was to observe these gamma ray bursts, to try to get a better understanding of the progenitor of these bursts, like what actually causes them in detail, and why are some bursts shorter than others? Does that mean the source is different? And if it is, what is the nature of the source? This telescope had done a lot of groundbreaking work. The problem is that this telescope, which is on a fairly sort of low orbit, is on its way coming back down due to the fact that it interacts ever so slightly with the Earth's atmosphere. And the way to think about it, the Earth's atmosphere is not like you go up a certain height above the ground and all of a sudden there's no atmosphere. The atmosphere is diffuse.
Yeah.
It's a breathing sort of beast. It's what you can think of it as.
Yeah, depending on the solar flux and all that sort of thing.
That's the thing. When there's a lot of solar activity, the atmosphere absorbs or interacts with more energy, and that tends to cause it to expand. Mm-hmm. And then when there's less energy coming from the sun, let's say during times of solar minimum, the atmosphere shrinks. So it's this breathing, alive, dynamical sort of thing, if you like. That's the way you're thinking about it.
And even the ISS has to be boosted back up into its orbit, because while there is very little atmosphere there, over the course of a year, it is non-negligible.
Yes. And so what happens essentially is it's the satellite or the observatory is experiencing essentially friction.
Right.
And it's causing it to drop down in height. And eventually it'll get too much into the atmosphere that'll just burn up and re-enter. This is actually forecast to happen for this particular observatory by the end of this summer. I mean, and there's an uncertainty on there, right?
Right.
Plus or minus a couple months or so. In fact, we've had cases, in the past, people may remember, where different satellites or spacecraft were re-entering, and everybody said it should happen around this time, and it's like media attention. And sometimes there's always an uncertainty on those times of re-entry, right? Because you don't know the exact state. You keep updating your time of re-entry as you get closer and closer to the time that it actually occurs. So this one is due to happen late summer, maybe early fall at the latest. And it's a shame because it was a great working observatory. It just happened to have been caught up in a situation where the atmosphere expanded more than what we had predicted due to solar activity, and it's coming down a little earlier, but ultimately it would re-enter anyways. That's just the type of lower to orbit.
In fact, I think there's treaties about that anything a country launches has to have some means of controlling re-entry, basically so we don't get Skylab dropping on houses again.
Yeah, and in most cases you try to drop them like in the Pacific Ocean, where it's easier to hit than a lot of other places. Now, the interesting thing about this story is that Catalyst Space Technology decided to try and save this observatory. And how they're going to save it, and you can see an image there, is they're going to launch, and right now the launch is scheduled just for a few days from now on June 27th, if it doesn't change. They're going to go up eventually to the observatory with robotic little miniature arms, and they're going to dock. They're going to rendezvous with the Swift Observatory, and then boost it into a higher orbit.
Cool.
To save it, so it has a propulsion system on board, so we can put it into a slightly higher orbit, at least enough that'll save it for several years. But the really important thing of all this is this could be the wave of the future. Mm-hmm. Instead of allowing workable equipment to fall down and then get destroyed, we can actually reboost them, put them back into a higher orbit, and if it's worth the cost, I think consider building a whole brand new spacecraft and launching it, and it's all costs a lot of money, then this is something that we could use over and over and over again. In fact, you can think of, the Hubble, right? Wouldn't it be nice to go to the Hubble, repair it, and then boost it into a higher orbit so that we could use it for several more decades to come? And it's still running, it's still doing great, but a lot of the equipment is failing, and we really need to do a mission to do that, to service it, and people are talking about that now. So we'll see how that happens.
We'll see how that goes. Yeah.
So this particular spacecraft is not a large spacecraft, so it can be launched on as cheap as possible. And how it's going to be launched, and this is an interesting technique, is going to be launched on what we call the Pegasus XL rocket. Now, in this slide, you can see an airplane, the L-1011 that Northrop Grumman has, known as the Stargazer. And underneath on its belly, you can see the Pegasus rocket. So what happens is that the main airplane flies up to a certain altitude, and then the rocket drops off the bottom of the airplane, and you already gain, let's say, 35,000 or 39,000 feet, whatever the height would be for these type of launches, and then the rocket takes off from there. So you don't need as powerful a rocket compared to if you were launching from the surface of the Earth. You already have that benefit of having, let's say, 35,000 feet in height before you then take off. And because of that, you're able to get a low mass object into a low Earth orbit, like the situation here.
Let's be real. The reason it's low mass is because it doesn't need anywhere near the amount of fuel. And people forget that your gasoline in your tank has a weight. The gasoline in that or not the gasoline, but the fuel in that rocket has a weight and keeps it. You have to lift that weight along with the rocket. So if you can get up above most of the atmosphere, like a plane can, you need less fuel to get on higher into orbit.
Now, to give you an idea of what is expected, excuse me, here's a slide showing you the rendezvous of the Link spacecraft with the Swift Observatory. So this is artist drawing, of course. And what you see there, so on the far left is the Link spacecraft as it's approaching. You can actually see its illustration of the robotic arms sticking off to one side. There looks like 4 of them in that image. And then in the middle panel, you can see it approaching the Swift Observatory, and then in the right panel, actually docking with it. And then at that point, it would fire its thrusters and then boost it into a higher orbit. So the first few weeks are going to be spent checking out the Link spacecraft. So it's going to make sure its propulsion system is working, the robotic arms are working. And of course, you can see there it has these solar panels that will provide electricity. And then it'll move in towards the Swift Observatory to try to dock with it and do its boosting into a higher orbit. Now, remember, the Swift Observatory wasn't built for this to happen.
No.
Right? This is all new. So they had to gear up an attachment mechanism for this Link spacecraft so it could successfully grab a hold of the Swift telescope and therefore move it into a higher orbit. So that's kind of one of the biggest uncertainty. Assuming that the Link spacecraft works perfectly, is how well are you going to be able to grab a hold of the telescope so that everything is stable enough that you're able then to place it into a higher orbit.
And how will the structure of the Swift telescope hold together? And will you be able to detach after you attach? And this will be interesting.
Yeah. So this is going to be cool. So this will happen later on this summer, and hopefully everything. So the launch occurs in late June here, and then maybe sometime in July. Then we'll be able to see a lot of cool stuff happening. We should get a lot of good information on what's going to happen by then.
I hope it works, but even if it fails, we will learn a lot from trying this. So,
And we'll make that promise today, Robert. We will report as soon as we hear anything about
Yes.
how well or not the mission goes.
absolutely.
So and it's,
Yeah.
Now, we do have a question from the chat from Extra
Okay.
Bola. So Extra Bola says, I saw a video the other day talking about how Sagittarius A star might not be a supermassive black hole, but rather highly compressed dark matter. Thoughts? Now, first of all, Sagittarius A star, just in case you're not familiar with what that is, that's essentially this very center of the Milky Way galaxy. And it's really difficult to map out what happens at the center because it is an area of the galaxy which has a high density of material. Okay. And so, but there are sort of regions, Botta's window, if you're familiar with that, where we can get a much better view of what's happening near the center. It's like a clearing, sort of a line of sight that passes through a low density of interstellar gas and dust. But most of these observations, when you try to map out the center, are done at long wavelength, like infrared or radio.
Radio, usually, yeah.
Yeah, so I can think of it like infrared, like the Keck telescope. In fact, the people that used the Keck won the Nobel Prize in Physics just a couple of years ago for mapping out and watching the orbit of stars near the center of the Milky Way. And from essentially Kepler's third law, you can ultimately calculate what is the mass that's at the very center of our galaxy in which there doesn't appear to be any light that's emitted. And that number comes out to be about 4 million times the mass of our sun. And you might say, what's the mass of the sun? So it's one of these numbers, right, that you remember as an astronomer. It's about 2 times 10 to the 30 kilograms. What does that mean? That's essentially 1 followed by 30 zeros in kilograms. It's a huge number. I wish I had that many pennies in my bank account.
And if you must use pounds, a kilogram is about 2.2 pounds.
Yeah.
So,
and there's an object that has 4 million times the mass of our sun. So 4 million times 2 times 10 to the 30 kilograms. It's a beast. It's a monster sitting at the very heart of our galaxy. And because it's so massive and it's confined to a very small area or volume of space and doesn't give off any light, the idea is that it is a supermassive black hole. In fact, we no longer speculate about that because we've taken an image of the shadow of that black hole.
Right.
See? Now, the idea is that from the paper that Extra Bull is referring to is maybe it's just a lump of dark matter. And dark matter brings in the concept is, okay, so like roughly 25% of the mass energy density of our universe is in the form of dark matter. And you might say, okay, what's that? We don't know. All we know is its influence via gravity on things that we can see, like stars and so on. And what we observe is seems to be this matter present in our universe, in our galaxy and most other galaxies, and it's affecting the orbital motion of normal things that we can see. And we can infer then, based on the fact we know how gravity works, and you can use the general theory of relativity, and you don't really need it for this, because you can simply use Newtonian laws to describe what would be the mass and the distribution of this dark matter. And it seems to permeate through the Milky Way and most other galaxies. And what you could do, this, as far as we can tell, this dark matter doesn't emit light, it doesn't absorb light, it doesn't reflect light. And in fact, the only way we know that exists up to this point, it's through its gravitational interaction.
Right.
So you could have a clump of highly compressed dark matter sitting at the center of the Milky Way. It would not emit light. It would be confined because it's highly compressed into a relatively small volume of space to the point where it could weigh 4 million times the mass of our sun. And so what you would do in that case in science would be, if it's a black hole or if it's a clump of highly compressed dark matter, are there any type of observations that I can make that would rule maybe one out versus the other possibility? And that's the kind of things you look for, is from a theoretical point of view, tell me what are the things that me as an observer would look for in order to rule out that it is a highly compressed clump of dark matter? Or what are the things that I need to look for that would tell me that no, it's consistent with being a supermassive black hole?
Right.
And that's kind of how science works, right? That's the way we use it.
And to me, it's irrelevant because it would be a black hole, because even dark matter, that much of it in that confined a space that we know it has to be confined into, would produce a mass energy density that's high enough to produce an event horizon, hence a black hole.
And the other thing, the other thing you can think of too is, how do you know that not in the early universe there were a lot of clumps of dark matter that collapsed to form black holes?
Right.
They're not necessarily formed of, ordinary matter, which we call like baryons, neutrons, protons, what we're made up of. They're actually formed of mostly dark matter. And that's a possibility.
That is a possibility.
We can't rule that out. Now, we do also have a question in the chat from Wondergoon.
Okay.
And he came in a little late on the podcast, and he's asking, is this a replacement for the Hubble? That is the Swift Observatory. Actually, no. The Swift Observatory was constructed to be sensitive to gamma rays, to examine what we call gamma ray bursters. So it is not a replacement for the Hubble. You could argue that a replacement for the Hubble was a bit of the James Webb Space Telescope, but that's mostly infrared, and Hubble does have capability to observe at infrared wavelengths. But the other thing that's interesting is that we have a new telescope that's going to be launched in August. And in some sense, you could argue that is really a replacement for the Hubble Space Telescope. And I don't want to go too far along to talk about that, because I was actually going to dedicate a different podcast to that as we get closer to the launch date. Cool. So maybe we'll use that as a cliffhanger for later type of thing. Okay. Now, Robert.
Yes.
Speaking about dark matter and the fact that it makes up 25% of the universe, what does the majority of the universe consists of?
Hydrogen.
No, I'm talking about all things.
Oh, then the majority would be whatever the heck dark energy proves to be.
Dark energy. It makes up 70% of the universe.
Right.
In terms of its mass/energy composition. Dark energy. Now, dark energy has been in the news the last year or two because of results from a new survey that were released called the DESI survey, the Dark Energy Spectroscopic Imager, or something like that, if I remember right. And what that is a 5-year survey, and now it has actually been extended a little bit to map out the location and 3 dimensions of a large swath of the sky. And how you do that is you have the spatial X and Y position on the sky. The thing that you don't know is the depth. Mm-hmm. So when you look out at the sky at night, you're really seeing a 2-dimensional representation of 3-dimensional space, right? You don't have the sense of that depth. To get the depth, that 3rd dimension, we use spectroscopy, and we use the fact that the greater the distance is to a galaxy, the faster it's moving away. So once again, essentially, we can use that Doppler effect that we talked about earlier in the podcast. So we can map out, therefore, the 3-dimensional location of objects in the universe, galaxies mainly. That will allow us to understand the underlying structure of the distribution of these galaxies. Now, the majority of the universe is composed of this dark energy. What is that? That was the discovery made in 1998 that the expansion of the universe is actually speeding up. It's accelerating, not slowing down, which was what everybody essentially thought at the time when this result was announced. And why would you think it'd be slowing down? Because imagine coming out of the Big Bang, the universe is in a state of expansion. By the way, we don't know why it banged, what banged, these kind of things, or what happened,
even calling it a bang,
or
is a
what
misnomer.
happened before the bang. The Big Bang is a theory that describes the aftermaths, really.
Right.
So it's kind
Like
of,
I said, it's not an explosion. It's the universe being, so it's a misnomer all the way around.
and so the universe is in a state of expansion. We can observe it. You don't have to believe us. Go to anyone with a large enough telescope to map this stuff out. It's there for all to see. But the surprising thing in 1998 is that the expansion rate is speeding up. If it was expanding, then because gravity is always an attractive force, right? So it comes in one flavor, unlike ice cream. That
or electromagnetism.
Right. Over time, you'd expect that this expansion rate would be slowing down, slowing down, slowing down. And the real question was, prior to 1998, is how much will it slow down by? For example, if you have a lot of energy and mass in the universe, it might come to the point where the expansion actually stops and maybe then reverses. So that the universe then collapses in on itself ultimately, the reverse of the Big Bang. Or maybe there is not enough matter and energy in the universe to halt the expansion. The expansion rate would slow down, but it would just keep going. It would expand forever. So the thing that we wanted to do in the late 90s is to use the best equipment we have to try to measure then how is that expansion rate changing? How much is it slowing down by? What is the deceleration of the universe? And lo and behold, what we discovered was it's actually accelerating. So this was something totally new. We put a label on that, dark energy.
Dark energy.
That's 98, Look at how many years it's been.
Right. And we're still looking.
And we're still trying to understand it. Yeah. And so this recent survey that's being done, the DESI survey, they reported results of the first analysis of 3 years of data. Remember, it's a 5-year survey. That 5-year survey has finished, but they haven't analyzed that. We're waiting and waiting, for next maybe half a year or so before we get the final conclusions from the full 5-year survey. But they reported a hint that the acceleration of the universe is actually slowing down. This dark energy component is getting weaker with time. And this is the first report of that. It's always funny. In science, right? After that result came out, now maybe it's a coincidence, but check me on this, Robert.
Okay.
Other papers were written using data from other surveys, and they were like mature, like this is like the 5-year data set rather than versus a 4-year or 2-year, whatever. And I started noticing that people were trying to fit. Now that's a sloppy use of term on my part, so watch out for that. They seem to try to be massaging the results so that there was more support for a changing dark energy.
Right.
And prior to that, prior to the release of the DESI results, people were suggesting, the dark energy is a constant. Mm-hmm. And if it's a constant, it's really adequately describe what Einstein did many years ago called the cosmological constant, where you got this uniform, constant density of energy from the dark energy, and it never changes as the universe gets larger and larger. And right away, of course, you jump on that and say, wait a minute, if the density of energy is constant as the universe increases in size, as it's expanding, that means the total energy in the universe is going up. There's no conservation of energy. And the answer is yes, you're right. There is no conservation of energy on that type of scale.
Right.
It doesn't violate, like general relativity. A lot of this conservation of energy business is more locally, and it's how you think about things. So you have to be very careful of that.
In fact, conservation of energy is really kind of weird because it's local. But if you get too local, like down on the atomic scale, we already know on the quantum level, it doesn't work. So maybe it doesn't work on the cosmological scale either.
So the results that were coming out, in other words, were trying to be consistent with a constant, the cosmological constant, right? Constant dark energy density. Yeah. But once the DESI results came out, it's like, oh no, then now you get this unconscious bias, I think. Right. So I think we have to be very careful in science how we jump to different conclusions. Let the data speak for itself. Try not to be influenced too much about what's out there and what seems like a more interesting, sexier result, right?
Right.
It's boring. Oh, I just found the same thing everybody else found. The dark energy density is constant. But if I, go this other route and say, wait a minute, it could also fit this if I kind of massage it a little bit. That's a more interesting possibility. Yeah. Now, what's happening in this paper that you see here on the slide is that the team of astronomers, a lot of which were involved in the early work that was done for the 1998 release of the discovery of the dark energy using supernovae of a particular type, 1A, they went through all of the sort of nuances of using supernova type 1A to estimate distances. And as part of this process of figuring out that the universe expansion rate is actually accelerating. And they went through all of the claims that have been put out there since 1998 that maybe would deteriorate the strength or the significance of these results. And they went through every one of it in a really detailed way. And what they came to the conclusion, this is the paper, is that no, that sort of result, they came out in 1998, that there is dark energy, and that seems to be a constant and not changing with time. The cosmological constant seems to be the best fit to the observations.
Right. Which would mean dark energy is then a property of space-time, in some way. But since is it?
Well, since we don't know what it is, it could be anything almost. Right?
Well, yeah, okay. In the end, yeah, it could be almost anything.
It could be still a property of space-time. It just changes, right?
Right.
For whatever reason, right?
Yeah.
Maybe there's an energy field associated with dark energy and it decays very slowly over time.
Right.
That can happen also.
Yeah, it's exciting times. We're finding out things. We're poking at things.
But it's nice because this paper is coming out and actually going against the little bit of unconscious bias where people are getting pushed into this camp of an evolving dark energy. Say, no, there's nothing wrong with the cosmological constant. Then we should be careful of all of this. Now, what's going to happen? Well, hopefully later on this year, we'll have the results from the 5 years of data from the DESI survey. And they will be able to say, no, what we thought with the 3 years was just a statistical fluctuation. That result went away. And you see that a lot happening when you have more and more data. Yeah. So we'll have to wait and see. Or if they do find something that's inconsistent, then there's some issue here that we need to look at in more detail.
Yep.
So who knows?
But this all saying it smacks of a familiarity in the fight between the Big Bang model and the steady state model after general relativity was shown to be the more accurate theory of how gravity works, because people wanted so bad that the universe is eternal and constant. Well, it's obviously expanding now, so how do we keep it eternal and constant?
I mean, it also points to the fact that there are a lot of uncertainties in science.
Right.
And what we're trying to do is come up with the best way of describing what we see. Mm-hmm. And that best way may change when we get new data.
Right.
And and as scientists, we are trained to be flexible. We let the data, lead us by the nose. Whether it goes to a place that we don't like or not, the universe doesn't care what we like or not.
Right.
The universe is the universe. And it's our job to try to uncover as best as possible what it actually is. It's fundamental true nature.
That's the plan.
Now, Robert,
at
some point, unfortunately, just like this podcast, we will end.
Yes.
Now, when we die,
mm-hmm.
Are you a cremation type of person, or would you like to have your remains put into a casket and for all eternity?
I guess I'm more cremation because, I have this idea of, plant me with a tree seed, an acorn, and let me grow, and you can't exactly do that anymore with a human body intact because you are labeled as toxic waste. Anyway, so cremation.
Cremation. Well, it doesn't really matter.
Right.
You know why?
Why?
Because up to now, the idea was when the sun naturally evolves, and becomes what we call an asymptotic giant branch star, it will swell up in size way beyond when it was a red giant, and it will essentially consume the Earth.
Yep.
So the Earth
So
will
you're
be,
cremated one way or another.
yes, the Earth will be cremated with everybody on board the Earth, whether it's your remains or there's
If there are
people still alive,
around.
in billions of 5 billion years from now, or whatever. So that's the idea, right? That's what
Right.
we thought was going to happen. Now, this paper, which just been published this year, actually says, we took a look at this idea. We looked in details of the model, and based on what we see, chances are that the Earth will survive the late evolution of our sun.
Oh, Lord, here we go again.
Now, the thing
This is a freaking yo-yo right here, folks.
exactly. Just wait another 3 years, and we'll be back to the Earth will be consumed by the sun's fires.
And the issue is that while the sun ages, it is converting mass into energy, so it's losing mass as it radiates. Well, that means Newton's universal law of gravitation. If the sun's mass is less, the Earth is going to move out away from it. So is that motion going to happen faster than the sun's expansion? And it's a yo-yo. It goes one way and then the other, and then the other way. So the answer is that it's a fine line. We're real close one way or the other.
Yeah, we're just happen to be at that right distance, like the Three Bears, the Porty,
Right.
right? It's just the Goldilocks zone, right? We're right at that spot where we can't really tell, right?
Right.
If we were a lot closer to the sun, then we knew for sure we'd be consumed. If we were a lot further away, then we know for sure we would escape that fate. But we're right on that boundary line, and the problem is, once again, uncertainties.
Right.
This paper is based on certain models. Those models are never going to be perfect. There's always things that are left out, or the input values are uncertain by a certain amount, and just tweaking something a little bit here and there, or not having the 100% of all the physics that's relevant may cause an issue and change the conclusion. Yeah, right. Exactly. So we just don't know, but it's interesting, right? We're going back and forth a little bit.
It could be the fact that the equations in that case do not have analytic solutions. In other words, exact solutions. They have to be solved numerically. Well, that brings in all sorts of which method of numerical solution do you use and what rounding errors and oh Lord, just wow.
Yeah, for sure. But someone stated on the chat, I wonder how much that study and paper costs. Well, I mean, that's how science progresses. Most of the papers, if you look at all the papers that are published in a given year, not to like I said, this is my own personal opinion, but not to rain on anybody's parade, the vast majority of the papers are boring.
Yes.
In other words, they add so little to the body of knowledge. There's only once in a while you get some really true, beautiful papers that really make a difference. But
that make you sit up and go, oh, wow.
Yeah, I better read this,
Yeah.
Back, from the cover to back, right? And sort of thing. But yeah, unfortunately, there is a lot. Have you looked at the number of papers that are published a year in astronomy and astrophysics? Tens of thousands.
Wow.
And
that's a drop. I mean, that sounds like a big number, but compared to some aspects of chemistry or something, yeah.
And you can ask me, for example, how many of those have I read from the beginning to the end? And it's a very small number. Why? Because by far the vast majority are kind of irrelevant to me in my research. What I do is look at the titles and skim through an abstract if the title is interesting.
Right.
Because I don't have time to read all those papers.
It's the same thing. We always have this saying, don't judge a book by its cover. But when it comes to books, you always judge a book by its cover. And the same thing is true of these papers. You read the title, it's interesting. You read the abstract, not as interesting as I thought.
Yeah, and the other thing is, if you spent all your time reading papers, you'd never do nothing. You wouldn't do anything new. No research.
But read papers.
So you got to watch out for that.
Right.
So don't think you have to do all this reading before you jump in the research. Learn stuff along the way as you're doing the research.
Right.
That's probably a better way of, doing some good quality work. Now, speaking about good quality work, the next slide I just want to show you, just kind of give you an idea of where we stand with the James Webb Space Telescope. Here is an image taken, a part of the Helix Planetary Nebula. This is so beautiful. I should have put like a side-by-side view. This is what we look at in the past. This is what we see now. The difference in resolution and clarity is just unreal.
Yeah.
Right? So this is looking in a planetary nebula. This is the end state of a low-mass star, stars that are less than about 8 times the mass of our sun. So that obviously would include our own sun. At the end of their lives, when they're in that AGB stage that we said already today, the asymptotic giant branch stage, they have a tremendous amount of mass loss. So the material essentially separates from the very core center of the star. The center turns into a white dwarf, and the rest of the material sort of floats out into space away from the central object. And what we're looking here is at one part of that planetary nebula. The central object is not in the field of view. By looking at the structure, you can tell it's sort of in the upper right, far away from what we're looking at here. But you see little knots, little pillars sticking out, and that's the erosion of the radiation coming from the white dwarf in the center that's pushing, it creates a wind essentially, you think of it that way, pushing material out away from the central region. And the higher density regions are able to survive longer than the lower density ones. So you get this kind of cool looking structure that forms.
If you live out in the country, you've seen this same type of effect. If there's a little rock sitting on top of piles of dirt, and it's due to the rain falling, and the rock doesn't erode, so it shelters the dirt underneath it, but everything else erodes. And I used to marvel at these types of effects when I was a kid.
Yeah. Now, John posed a question, how much of that nebula image is computer interpretation of the data from James Webb? None. It's a real image. It's not been processed at all except stacking images together, taking the different wavelengths, so you get that color information. But that's about it. There's nothing added here to change the information or anything like that from that point of view. So, yeah, so anyone who's interested in planetary nebula, here's what I propose you could do. Take this image now, and then take an image if the James Webb is still operating maybe a year from now or 2 years, and look for changes.
Yeah.
Because this thing is constantly changing. This is just a snapshot in time. This thing is very dynamic and evolving. And those changes can tell you a lot of information about how rapidly are things flowing away from the center and the interaction that occurs in the material. So
Another a really good, amazing, honestly, image that shows you this sort of thing is do a search for a Crab Nebula GIF.
Yeah.
And you can actually, when you run that video, essentially stacking of a few years worth of data, you can see the magnetic field of the pulsar inside the Crab Nebula sweeping through the nebula and disturbing it. And it's beautiful.
Yeah, you see a lot of like the Rayleigh-Taylor instabilities. In other words, you want to see a little bit of what's happening in the process, go get yourself a lava lamp. Mm-hmm. And that will show you, the kind of stuff that happens. There's a lot of different processes occurring at the same time here.
I will also point out this is why you want as big a mirror or as big a lens as you can, because these things don't appear until you have high enough resolution. It's not magnification, it's resolution. And to do that, you need a bigger light gatherer. Bigger eye.
Robert, we are running out of time now for the podcast. Would you like to close things up by talking about our home?
Sure. Let's do it.
Let's do that. So, go ahead, Robert.
I think you're referring to the other paper you came across and you threw at me. It's about the Earth's magnetic field and the flow of the outer core. Sorry, not outer mantle. The flow of the outer core's material, because it's that flow of that liquid outer core that produces the magnetic field. It's called a geodynamo. And we can map those flows by mapping the changes, the way the magnetic field strength and direction changes over time. And we can do that with ground-based observatories of the magnetic field or satellite. And this paper in particular used both. And what the interesting thing about it is that the flow under the of the core under what we see as the Pacific Ocean was slightly to the west, but a few years back, about a decade ago, it shifted strongly to the east, and we've been trying to figure out why. And this study used all this information to find that, one, that flow to the east is weakening, starting to turn back. But to me, the really interesting part of it was some of the graphs, the plots they made of these flows, because I immediately picked up what it looks like is if you've ever seen a whirlpool in like a bathtub or in a stream and you poke your finger in it, it breaks off and splinters into several smaller whirlpools. And these diagrams of the flows look like that. So as they propose, it's rather clearly that something disturbed those dynamic flow within the outer core. By the way, the outer core is the liquid iron. Through high pressure experiments, I always like pointing it out because I found it to be a neat point. The viscosity, how well it flows, the liquid iron there, is around that of water. So, the analogy of the whirlpool is not that far off. The core is spinning and the Earth's rotation causes it to rotate, but something is powering a tighter, more energetic spin, and it's that gives rise, that moving of the charged particles within the iron that gives rise to the Earth's magnetic field, and happy for it.
Yeah. And then Chuck from the UFO show asked, when did that flow shift? And it's right. It's around 2011. 2010, 2011 time frame is when it started shifting.
And they're still trying to figure out why it shifted. But this is a way of getting at that. So hopefully we'll get some more satellite data, some more ground-based data, and be able to start piecing together a clue, a picture of what was going on and what happened. Maybe we'll catch the next one, because as I understand from the paper, they had a blackout of satellite data at about the time it happened.
Right.
And that's unfortunate because the satellite data is actually more comprehensive.
Yeah.
And it's why we want magnetometers around Jupiter and Saturn and the moons of Jupiter and everything, is because we can start mapping these magnetic fields, how they're changing, how they're warping. And we know the physics of magnetic fields. I mean, we have since Maxwell's time in the late 1800s.
Yeah, and it's, of course, it's very cool just to think that here satellites high above the Earth's surface can tell us something fundamental, what's occurring deep inside the Earth. Deep inside,
because, again, we know what generates magnetic fields. It's just a question of how that one is working, and it's all encoded. We just got to pull the information out.
Yeah, that's what you call science, folks.
There you go.
Now, if you're interested in science, or if interested in any other higher education fields, one of the things you could do, of course, is come to the University of North Dakota. We do have programs that's available both online and on campus. And like I said, if you come on campus, you'll be able to see the beautiful STEM building that's rising. And one of the things you can do, of course, is to see Robert and I.
Absolutely. Come by and see us.
Have a good old chat.
Yeah.
Now, our next podcast, Robert, is next Tuesday, June 30th.
30th?
30th. Oh, yeah. So it's the last day of June already. So almost into July. Wow. And that's going fast, doesn't
yes.
it? That's what happens when you're on vacation. You're missing time.
Right.
Anyway, so next podcast will be the same great time at 8 p.m. Central Daylight Time.
8 p.m.?
What's that?
8 p.m.?
5 p.m. So did I say 8?
You said 8.
Well, it depends where you live. It could be 8.
I guess.
But it's not Central Time at that
5 p.m. Central Time, folks.
Yeah, 5 p.m. Central Daylight Time.
Yeah.
Now, we always leave you with a quote.
Mm-hmm.
And I'm going to do the same today, of course. It's related to the Swift Observatory. So the principal scientist of the Swift Observatory, Neil Gehrels, he's very famous astronomer, scientist. He was born in 1952, and unfortunately he passed away in 2017 from cancer, which affects, of course, a large number of people. And so NASA renamed the observatory in honor of him. And here's a quote from Neil. "Science is a team sport. It is the joy of working together to solve the puzzles of the cosmos."
Nice. I like that one.
Yeah, very cool. Thank you very much for watching. Remember to give us a thumbs up if you haven't already. Subscribe if you haven't subscribed. And we will see you next time.
Next time, folks.